Okay. Feeling a bit under the weather today, but have my halls, I'm all medicated. Ready to go. We're going to get this right. I told my two classes before, it's like this close to canceling all my classes today. I felt like, man, I know. It's a different ballgame though, you know? When your student in class gets canceled, you go, yeah, awesome. When your teacher in class is canceled, it's just stress, because now you're like, geez, am I going to finish the syllabus? When am I going to make up this class? How am I going to make up this class? You'd rather risk death than have to make up a class. You know? You're like, well, if I die, then I don't have to make it up. But if I survive, then there's this thing now. And it's like, yeah, so if I'm ever absent because I'm sick, you know it's like really bad. So we're going to talk about, hopefully by the end of today, 3 main things. So last time we kind of discussed the meaning of matrix multiplication. You don't need to know that. It was just an excursion in curiosity for anyone who was curious. But the last part of class is something that you need to know, the idea that we can represent systems of equations using matrices and manipulate these systems. Before we jump back into that, I just want to come up with some definitions, some more definitions that I need to tell you before we move on. And then we'll actually go back to that idea of manipulating systems with matrices. Or I should say a zero matrix because it depends on the size. That might seem obvious. There are contexts in which this is not true, but for this class, this is how we'll define a zero matrix. You can have zeros of any size. When the size is understood, I would tend to denote it with a 0 with a little vector on the arrow. So I can, or I might even tell you the size of the zero matrix I'm talking about. So you can have like a 1 by 1 zero matrix, or a 2 by 2 zero matrix. 2 by 3 zero matrix, doesn't matter. If it's a matrix where everyone is 0, that's called a zero matrix. And for emphasis, if it's not understood, I'd set 0 equals, and I'll describe to you that I'm talking about the 2 by 2 zero matrix. That's a very important idea. Helps us with addition a lot of the times. Another thing you'd want to know about is something called a diagonal matrix. This is a matrix. This is a square matrix. In which all non-zero elements if any, appear on the so-called main diagonal. Oftentimes we leave out the word main. Someone says diagonal, they're talking about this one. That's from top left to bottom right. So a zero matrix is a diagonal matrix. This guy is a diagonal matrix. Let's see. This guy is a diagonal matrix. So basically, if you look on the main diagonal, it's that this the set of numbers that go from the top left to the bottom right of a square matrix. if you notice that literally everywhere except that strip has all zeros, we call it a diagonal matrix. If a non-zero number shows up, it has to be in the strip. We call these guys diagonal matrices.
So it can't be diagonal like this?
No. Right. So top left to bottom right, this is the main diagonal.
What does it say after elements?
If any. Meaning that if there are non-zero numbers, they have to show up somewhere other than on that strip. So here, there are no non-zero numbers. It's still considered diagonal though, because everywhere other than that strip is zero. Now there is one important kind of diagonal matrix. It's called the identity matrix. And even that, I shouldn't really use the. It's, you can have many kinds. Really the wrong word here. But this is a diagonal matrix. With all diagonal entries equal to 1 specifically. So if you take a diagonal matrix and make sure everyone in that strip is the number 1, you create what we call an identity matrix. So the notation is the letter I. So every time you see me do a capital I in a matrix context, I am referring to this matrix. There are times when we're going to talk about things like inverses, and in the past I put I in a problem and students think that's the inverse. You'll never need an inverse. Capital I always means this guy. He's very important. And we reserve the letter I to refer to this guy. He's that important. Or we might do I sub n if size isn't obvious. So for example, if I refer to I1, that's just a 1 by 1 identity. I2 is the 2 by 2 identity. I3 is the 3 by 3 identity. Etc. Right? So if someone says IN, they just mean you have an n by n matrix where there are 1s all the way along the diagonal or zeros everywhere else. Sometimes for short, we might do this kind of an idea, but it's understood. You write like what you want the diagonal to behave like, and you write like a big 0 to represent that everywhere else is 0. Right? So kind of informal, but it's standard to do things like that. So this is basically saying that along the main diagonal we have all 1s, but we have zeros everywhere else. And if this has n rows and n columns, we call it IN. So this guy is always a square matrix with 1s on the main diagonal, zeros everywhere else. Now we saw this guy show up last time when we were solving the system, and that's one of the reasons why this guy is important, but there are many. Here's an example. Let A be 1, 2, 3, 4. Let's go for 1 minus 1. Okay. Now find I2 times A. Do this one. B. Find A times I. Now let's see who's paying attention. What size does I have to be if I put it on the right? Has to be a 3 by 3, right? Why? Because A is a 2 by 3. So I know this, I2 means 2 by 2, this is 2 by 3, so that makes sense to multiply in this order. This is a 3 by 3, that's what makes this match up. So the size might change depending on what side you're on. The only identity matrix that will do for what I'm going to show you that this does. And the same one you can put on either side is when the matrix itself is square. Then the same identity on both sides will do what I'm about to show you. Here is, and this is why it's called the identity matrix. When they mention identity, they really mean the multiplicative identity, kind of like how 1 is the multiplicative identity for the real numbers. In what sense? Let's see. If I look at A, which is this, notice that this just means 1, 0, 0, 1 times. I'm going to assume we all practice matrix multiplication over the weekend, so I can kind of just jump into it at this point. We're going to first row times first column, first row times second column, first row times third column, and second row times first column, second row times second column, second row times third column. If we simplify this, you'll notice that gives us 1, 2, 1, and 3, 4, minus 1. Now what's that? That's actually the original A, right? So if I take this guy times any matrix, the result will be the identity of the matrix I multiplied that guy by. This is why it's called the identity matrix. Kind of like the same thing with real numbers. 1 times any real number is just the identity of the real number. This guy is like the 1 in the land of matrices. And he isn't unique. Matrices have multiple 1s, depending on what size you're looking at. But there are a bunch of guys that act like the 1 that we know from real numbers. Similarly, on the other side, you'd actually notice something very similar. So if I do that, 1, 2, 1, 3, 4, minus 1. First row times first column. 1, 2 times 0. First row times second column. 1 times 0. 1. First row times third column. Down second row times first. Second row times second. Second row times last. And if I simplify that, again I'll find a 1 here, 2 there, a 1 there, a 3 here, 4 there, and a minus 1 there, so I get A again. So that's why it's called the identity matrix. It gives you the identity of anyone you multiply it by. It's like the number 1. So this means that if A m by n is a matrix, then I don't know if you can call this a theorem. It's probably not heavy enough to be called a theorem, but whatever. If A m by n is a matrix, then if you take I m times A, you will get A, and if you take A times I n, you will get A. And I n A equals A I n equals A if A is squared. And that's why it's called the identity matrix. It gives you the identity of anyone you multiply by. Now that is super useful.
Can you take a picture so okay, thank you.
Now here is, I want to tell you about this right now. Yeah, might as well. I'll tell you about it right now, and we'll come back to it. But just to introduce the idea, the inverse of a matrix, also a very, very important idea. We're going to use this idea, and I'm going to tell you specifically how to find it. For now, I'm going to tell you what it is. Let A n by n be a matrix. I want you to pay special attention that I am talking about a square matrix here. What I'm about to say makes no sense for anything that's not square, because you kind of need this idea to happen. You need to have the same guy work on either side. If there is a matrix B such that 1 A times B equals I, and at the same time 2 B times A equals I, then B is called the inverse of A. Now the name is, again, kind of because we're trying to model something from the real number system. So we understand that matrices aren't real numbers, but we're kind of seeing what properties do they have that real numbers would also share. So what you might want to compare this to is the idea of looking at inverses for the real numbers. So CF, compare this to, we know that 2 is the, or you can say 2 to the minus 1 is the inverse of 2, since if I take 2 to the minus 1 times 2, I get 1, which is the identity for the real numbers. And if I take 2 times 2 to the minus 1, I also get 1, which is the inverse of the real numbers. This property allows me to call this guy an inverse. Now in the reals, 2 to the minus 1 equals 1/2 because of laws of exponents, right? We want to capture this kind of idea with matrices. Do matrices have a similar kind of pattern to them? Does division work with matrices? Does this actually make any sense? So that's the comparison we want to make. In the above, we denote B equals A to the minus 1. Okay? And it's very important that you realize that this is a notation. A to the minus 1 does not mean 1 over A. In fact, this is meaningless. I'm not sure I'm going to fully explain why that's meaningless, but I'm going to give you some hints as to why it's meaningless. So this guy really means the inverse of A. It's a notation for the inverse of A. Or informally we call it A inverse. And that notation will always mean the inverse of A. So, i.e., if I take A times A inverse, I will always get the identity. And if I take the inverse times A, I will always get the identity. The inverse is just a matrix that makes these two true. We'll talk about where it comes from and how to compute it later, but for now just know what it is. And there's also a theorem that says the following. If 1 is true, let's call this 1, then 2 is automatically true. So you only need to check one of these if you're in the situation. So there are a couple things I want you to appreciate. If a matrix is not a square matrix, this property will not hold. Because you won't be able to multiply on both sides because the numbers won't match up. So this is not something that you can do in general. You should also be aware that there are matrices in which you can actually do this anyway. So there's some notes here. If you're not square, there will be no matrix A inverse that does this property. And 2, even if you are square, some matrices still don't have this. I can give you a couple of examples. The zero matrix will not have an inverse. For a non-trivial example, let's say I just put a 1 in the top left corner. That also will not have an inverse. I'm going to prove this real quick, but again, it's not really something you have to pay deep attention to at the moment, because I'm going to revisit the topic of inverses. I just want to throw out this definition out there so that you know, you're aware that there is something out there like this. There's going to come a point in our journey where it's important to talk about it. And when we get to that point, I'll revisit it. Suppose 0, 0, 0, 0 has an inverse. Well, that's pretty easy to actually show or check because this means there's a matrix. Let's call it A, B, C, D, so that if I take this times A, B, C, D, I will get this, right, by the definition. Now, would that ever happen? Can I pick numbers for that to happen? Well, if I apply the rules of multiplication, row times column, I would get 0 times A plus 0 times C. Row times column, I would get 0 times B plus 0 times D. I would get 0 times A plus 0 times C, 0 times D plus 0 times D. And that would give me pretty much 0, 0, 0, 0. There's no way to get this. These will not be equal. Meaning, there is no matrix that you can think of that will do that for this guy, right? So this guy, we say, does not have an inverse. Or we say he's non-invertible. Or we say he is singular, would be the name for it. I'll remind you of that term when we get to it. later. If we suppose the same thing, we might be able to say, well, maybe if one of the numbers aren't 0, we will get away with it. It will have to be a 2 by 2 because that allows us to multiply another 2 by 2 on either side. Then if I have 1, 0, 0, 0 times A, B, C, D, this is going to give me, well, 1 times A plus 0 times C, and 1 times B plus 0 times D, and 0 times A plus 0 times C, and 0 times B plus 0 times D, and that will work out to A, B, 0, 0. That's never going to be equal to 1, 0, 0, 1, because by equality of matrices, that's not a thing. Matrices are equal when their corresponding components are equal. 0 is never going to equal 1. So this matrix also doesn't have an inverse. And you might say, well, Jhevon, you're just cheating. You're just putting a lot of zeros. I can give you another example. Also has no inverse. Left to the reader to verify. So it's not just, oh, you're just cheating because you're putting a bunch of zeros, so we can't get it. You don't need to actually do that. So inverse is a thing that some matrices have, a very select few matrices have. We call these the invertible or non-singular matrices, which is why division as a categorical operation does not exist. Because when we talk about real numbers and we talk about division, you can pretty much divide any real number by any other real number except the number 0 itself. When it comes to matrices though, this is a much more selective process. It's not something you can just, as long as it's not 0, you can divide by it. No, it actually isn't true. There are a bunch of things that there is no way to divide them. It would make no meaningful answer. And so division isn't a thing with matrices, it won't work. And you can also think of division as the reverse process of multiplication. And basically, you will be able to see with this matrix, if I use that and multiply anybody, there's no way to reverse that process to recover the original matrix. Like if you tell me this information, I have no idea what the original matrix that I multiplied by in the first place would look like, right? Division means it's a process that we can reverse. And for matrices, that doesn't always work out. So we just have to be like, yeah, division isn't a thing. It's not a thing anymore. It was a luxury when it came to real numbers. It's no longer a luxury. Matrices, they don't know what you're talking about. Talk about division. So that's the first thing. Let's kind of segue into where the last class left off. I think that's all the preliminary. Well, 2 more definitions. And then we move to where the last lecture left off. Where I will do, in fact, more definitions. We need the language to be able to talk about this stuff, so I have to give you the vocabulary of what we call certain things. Definition. The transpose of matrix. This is useful for some of the formulas that we'll be looking at. This is the matrix obtained by interchanging the rows and columns of a matrix. So you have a matrix, turn the first row into the first column, turn the second row into the second column, turn the third row into the third column, etc. You do this process, you'll create some other matrix. This is called the transpose of the previous matrix. So if A is equal to say 1, 2, 3, 4, 5, 6, then if I were to take the first row and turn it into a column, take the second row, turn it into the second column, that creates a new matrix. You should notice that the original matrix is a 2 by 3. The transpose becomes a 3 by 2. It literally swaps the rows and columns. And we call this guy the transpose of the original, and that's the notation. So this guy is the transpose of A. Or a transpose, informally, but it's colloquial. So when I say A transpose, I'm referring to this guy, and that guy just means take the original A, swap the rows and columns. I don't remember if we'll need this, but just in case. The trace of a matrix. Is the sum of all diagonal entries. So for example, if I have A equals 1, 3, 1, 0, minus 1, 2, 1, 1, 7, then I can say the trace of A, this is the notation for that, is going to be me adding up all these diagonal elements here. Remember the guys on the diagonal, or these guys? That's going to be 1 plus minus 1 plus 7 equals 7. And I call this guy the trace of A. So we know what a zero matrix is, what an identity matrix is, what a diagonal matrix is, what the transpose of a matrix is, what the inverse of a matrix is, and what the trace of a matrix is. These things will become important later when things start getting a little bit more complicated. At this point, it's not really something to understand, it's just something to know. This is what we call these things. It's just definitions. It will help us to talk about certain other things. So, last time, now we're back up to speed where we left off last time. We saw matrices can be used to represent systems of equations. I didn't write this out generally, but I did some examples which hopefully makes the idea clear. I think it makes it clear when I write down the examples. For this class, writing down everything too general just makes it overly complicated. But for other classes, I probably have to write things down in general. So for example, I can have a system like ax plus by, cx plus dy equals ef. And I can translate that to matrices by looking at that. Matrix multiplication tells us this is equivalent to saying that, and this is called, so this is a system of equations. Which is a very simple object. Most of us saw it in algebra class, but it's actually highly useful in like you go to the highest levels of complicated mathematics, there's going to be a space somewhere for these guys, believe it or not. A lot of linear equations are extremely useful and applicable. This is called the matrix equation for the system of equations. And the generic notation for this guy, we looked at it. So we're still in the recap phase. Is we sometimes refer to this as AX equals B. So anytime I write that phrase down on the board, I'm thinking of an object like this. There's a matrix times another matrix that has all our variables equal to some matrix with a lot of numbers in it. This expression means I'm thinking of something like that, where the A can be any size that makes the system actually work. Now, if we write this as in the form A, we put a line and then we put the B. We say we've augmented the system. So for the above, for this situation, I can just write one big matrix with the A, B, C, D, which is the A. I can write a line which represents the equal sign, and then I write the E and the F on this side. And it's kind of understood without being stated that the first column deals with your X and the second column deals with your Y, but I'm not writing it down. And this is called an augmented matrix. So sometimes I'll give you a system and I'll say augment the system and use row reduction to solve the system. This would be the first step of that process if I ask you such a process. Now, last time what we also did was we actually did this for a system. We did a bunch of mumbo jumbo with the matrix and we got it to a form where we could see that, oh, 1 times x plus 0 times y equals this, and 0 times x plus 1 times y equals that. And we could find the solution to the system. We could find the x and y's that make the entire system true. Now that process that I did, last time we did a process to solve the system. What was the system? Was it x plus 2y equals 3, and I think it was, what else, 2x?
Minus 3y equals to -1.
Equals -1. And we got that x equals 1 and y equals 1 was the solution. But remember what we actually did is we augmented the system. We did a bunch of stuff. We ended up in a situation that looked like 1, 0, 0, 1 with 1 and 1. No. It should not be lost on you that the identity matrix shows up over here. That is what made it very convenient. But this process that we did, the process is called row reduction. That's what it's called. Or some people just say elimination when we know we're working with matrices. So I say augment the system, solve it using row reduction. I mean, I wanted to do what I did at the end of last class. That's what the instructions mean. Now, this, as you might see, was not an unguided process. there was a certain kind of situation I wanted to induce. A situation where it was clear to me by reading off the matrix that I could tell what x and y are. Now, not any arrangement of numbers could actually accomplish that. If it could accomplish that, I probably would have been able to do it from up here, but I wasn't. I put it into a situation where actually seeing the answer was easier for me. And so there are some convenient situations to be in. And these guys are what's called the echelon forms. I don't remember where the etymology of that word comes from. What echelon means. Probably means something useful in some other language like German or Latin. Whenever you see a non-obvious name, that's usually the case in a math context. They just decided to use a German or a Latin name to describe something. But that's what it's called. So this form is called an echelon form. There are two such forms. I'm going to describe them to you, then we're going to look at a bunch of examples to see if you can recognize them. So one is called the row echelon form. Because I'm lazy, from time to time, I will abbreviate this as REF. Now, I did mention this last class as well. Right now, we're going to get to definitively what this is. Here's how you know when a matrix is in this form, right? What we call the row echelon form. 1. I should probably explain the is moved to the bottom a little bit more, but we'll get there. 2. The first non-zero number in any row, if there are any non-zero numbers, is a 1. Specifically the number 1. This is called a pivot or leading one. So you'll notice that that was achieved here. If I look in the first row, the first non-zero number I hit was a 1. If I look in the second row, the first non-zero number I hit was a 1. Right? So this matrix fulfills that criteria. There are no rows of zeros. If there were, they would be at the bottom. And the first non-zero number in every row should be a 1. So that's 2 criteria for the row echelon form. The third criteria. Each pivot goes without saying except the top. Should be to the left of pivots above it. That's the third criteria. Notice that, that should be right. Notice that this guy's the pivot in the first row, this guy's the pivot in the second row. notice that the pivot in the second row appears to the right of the pivot that's in the row above it, right? So you kind of want the ones to cascade off to the right, right? In other words, you kind of want the matrix to look as much like the identity matrix as possible. That's kind of the idea here. Now the ones might not be right beside each other, but whenever a one shows up, it needs to be on the right of any ones that are above in the above rows. Essentially what we're trying to do is create a situation where the identity matrix is on the left, or if that's not possible, because it's not always possible, we want to get as close to that situation as possible. That's kind of the goal here. And 4. Each pivot has zeros below it, except the bottom one, of course, because there's nothing below the bottom one. Now you'll notice there's nothing below this pivot, so that requirement doesn't apply. However, this pivot, there are rows below it. What you should make sure is that everyone underneath that pivot is a 0, right? So pivots have zeros underneath them the whole time. That's it. This is called the row echelon form. Any matrix you look at that fulfill these 4 criteria, we say it's in row echelon form. Yeah.
So the matrix can only have zeros below them, right?
Yes.
And then also.
Yes. In the case that you don't have 0 below it, you have not achieved this form.
Okay. And so if it's like they always have to be to the right of the one above them. Like what if
Yes.
they're like in the same row but they're all the way to the right column? That would be in row echelon.
That would fulfill the criteria.
Okay. So like what if they were like in the last column?
I'm gonna do examples, but
Okay.
let's say you had something like that. That's in row echelon form.
What if you had another one in the very bottom right?
Right here?
Yeah. That would not.
No. Because here, this guy is the first non-zero number in a row. He has to have zeros below him.
Oh right. Yeah.
Right. That would. I mean, we're gonna do a bunch of examples. There's a point to this rigorous definition. Okay. So that's called the row echelon form. There is another convenient form. And last time we did an example, I actually marked off a point that I labeled the row echelon form. I didn't tell you what it was. But you can actually look at that point on the last example of last class, and you see that that situation fulfills this criteria. The second most convenient form is called the reduced row echelon form. Which, when I'm lazy, I'll refer to this as RREF. And guys that are in this form are guys that they're already row echelon form, but you push it a little bit further. So 1, it is already in REF. With an additional criteria. So 1 additional criteria separates a row echelon form from a reduced row echelon form. And this criteria is the following. Which you can probably tell from last week's example again. What was the difference between the 2 forms that I labeled? What was the difference between the 2 forms I labeled? The pivots also had zeros above them. So the column that a pivot shows up in, that pivot must be the only non-zero number in that column. So pivots except the top one, of course, also have zeros above them. Also have only zeros above them. E, pivots are the only non-zero numbers in their column. It's very important that we understand these forms because I will be requiring you to put things in these forms. So let's actually go through some examples. Wait till you guys copy that down.
Do these two forms, like all the criteria, do they count for the right side of the equation too? Like on the right side?
No,
of the
well,
line?
when you're putting in these forms, you kind of ignore the bar. Don't worry about the bar, where the bar is.
So the stuff on the right.
Yeah.
still
So
counts?
when you're talking about this, you're looking at the matrix on the as its entirety.
Okay.
I think most of it are done. Okay, let's make sure we understand what these guys are. It's going to be very important. Okay, so the question is it row echelon form, reduced row echelon form, or neither? So I'm going to write down a bunch of matrices on the board. You're going to tell me which form is represented by that matrix. I think I wrote down some examples. Yeah. Like I said, I want you to actually ignore where the line is. It doesn't matter for this, so I'm not even going to write them in for these guys. But even if I drew them in, it wouldn't matter at all to your classification. So if you copy them down, you can already start analyzing, kind of making your guesses. We're going to talk about them together. Okay. Okay, the first one. What form?
Okay.
This is R, E, F. This is correct. Any row of zeros will appear at the bottom. There are no row of zeros, so we don't even have to worry about that. The first non-zero number in every row is a 1. The ones appear to the right of the ones that are above them, and ones have zeros all the way below them. So that is REF. What's stopping it from being reduced or echelon?
So two.
The 2. If this 2 was not there, if this was a 0, then it would be reduced or echelon form. But for now, it is just row echelon form. What about this one?
Is that also one?
Huh?
Is that also one?
This is REF. Again, how do we know? You go through all the criteria. Any rows of zeros are at the bottom, doesn't apply here. First non-zero number in every row is a 1. The ones are to the right of any of these ones that are above them. So this one is to the right of that guy, this one is to the right of that guy. All the ones have zeros below them. So that is row echelon form. What's stopping it from being reduced or echelon form? Again, the 2, right? If this were 0, that would lead to a reduced or echelon form situation. This one. Right? This is a reduced row echelon form. Any row of zeros are at the bottom. First non-zero number in any row where there are non-zero numbers is a 1. The ones appear to the right of the guy that's above them. And all the ones have zeros below them. But all the ones that are not in the top also have zeros above them. So that's reduced or echelon form. This one? This is neither. Why?
So there's a 2.
Right, this 2 should be a 1, right? The first non-zero number in every row should be a 1. Here, that is not fulfilled. So that would have to be a 1, and if that were a 1, what would it be? It would be reduced, because all the 1s will be the only non-zero numbers in their column. They all appear to the right of the ones that are above them, etc. Yeah.
So in order to do echelon form, like it doesn't have to be augmented or square. It can be any type of matrix.
No, it's just the form is just like a form of a matrix,
Okay.
like in the general sense of the word. It happens to be very convenient when we're solving equations and there's a bar, but that's incidental. That's kind of the inspiration for the definition, but you don't need that for the definition. Right? When you look at a matrix, just see what criteria it holds of the ones I listed, and certain criteria indicate this or that. What about E? Neither. Why?
The one.
Because of this guy. This is a first non-zero number in every row in the row, but he's not to the right of the one that's above it. He's literally right underneath. So this is neither. This one?
Reduce.
Row echelon or reduced row echelon? This is reduced row echelon. This one? Why? Okay, here's a row of zeros smack dab in the middle of the matrix. Below it you have a row of non-zeros. So this is actually neither. This should be down here. If it were, that would be reduced, but it's not because it's not. This one? Right? Again, all zeros, rows of zeros are to the bottom. First non-zero number in every row is a 1. The ones appear to the right of the guys that are above them. The ones have zeros all the way below them. They do not have zeros above them, so that makes it not reduced. It's simply just row echelon form. Yeah.
So if you get a problem that has a matrix like G, like are you allowed to just rewrite it and like move that row of zeros down?
Yes, that is the next phase of the lecture. As you can see, last time I did an example where we started off with a matrix, we did a bunch of stuff and we got to a situation where it was in reduced row echelon form. So that process is actually a thing, and there are legal ways to get to this form and illegal ways to get to this form. So let's actually talk about that. But one thing, you need to recognize what the form is. So you know when you're trying to get there, you should know what you're aiming to get at, right? So I just want to make sure you know what you're aiming at. Now, how you get there is also very important. Legal is the right word here. So you might notice that we did things with rows when we were doing this. Like I told you, oh, I'm taking the first row and I'm subtracting it from the second row, or things like that. We were thinking in terms of rows when we were manipulating the matrix, as you may have recalled from the last class. Now, what made these legal? These coincided with processes we can do with equations in the elimination method. Referring to the elimination method that you remember from high school. When it's all said and done, there are three things you can do legally when you are trying to take a matrix that's not in one of these forms into one of these forms. They're called row operations. There are three types. Type 1 is called interchanging two rows. This is a thing you can do to manipulate a matrix at any given time. And in doing this thing, if the matrix represents a system of equations, you're not changing the solution by doing this. So one way you can see this is that if I have x plus y equals 2 and then x minus y equals 1, then I could write this as x minus y equals 1 and x plus y equals 2. And there's no difference, right? Solving this is the same as solving that. The order in which you write the equation doesn't matter. A system is a system. These are the two equations in that system. For whatever reason, I can swap the order in which I write the equations. It will not make a difference. Therefore, if a matrix represents a system, we saw that the rows gave us the coefficients. I can swap rows. So yeah, in the situation that was over here where we had the 0 in the middle, I could just swap row 2 and row 3 to achieve a reduced row echelon form. That was legal. This is one legal thing that you can do to actually change the form of a matrix without messing up the system that it represents. Here's another thing you can do. It's a type 2. You can multiply any row by a non-zero constant. And again, that's something you can do with equations. If I have x plus y equals 1, I can multiply both sides by 2. That's legal, right? The solutions to that are exactly the same as the solutions to this one. What's bad is if I decide to multiply everyone by 0, then I just get 0 equals 0. Now, how am I going to solve that equation? I've just eliminated all the useful information, right? So I can multiply a row by a non-zero number because it doesn't kill the information that I need to solve the system, and the solutions before will be the same. The solutions after will be the same as the ones they did before. This doesn't actually change the values of x and y. So sometimes you saw me actually do that. We took like -2 times this row for the purpose of adding it to another row, which leads us to type 3. You can add 2 rows together. Add or subtract 2 rows. Now, I'm going to state this in a peculiar way. Yeah, for this class, it's never going to matter that you do it in exactly this way, but it has to be stated in this way because there are contexts in which not doing it in exactly this way has consequences. So here's how it's stated. We can replace a row by itself plus a multiple of another row. Again, it's stated in a special way here because there are contexts in which it doesn't matter how this is done, but for us it's not going to matter. We did this again. We multiplied one row by -2 so we can add it to another row to create a 0 where there wasn't a 0, right? This is called a type 3 operation. There are only 3. Anything else you do with a system of equations that's not a combination of one of these 3 things or several of these 3 things is illegal and you did something wrong, right? When it comes to equations, there are certain things you can't do. So for example, you can't add 1 to all the numbers in a row, right? That wouldn't make any sense. Because if you take x plus y equals 1 and you decide, oh, I'm going to add 1 here, add 1 here, add 1 there, what you would have done is you added 2 to one side and only added 1 to the other side. Not legal. You changed the values of the equation, right? So you can't like add something to everybody or subtract something for everybody. Illegal. You've changed the system. But these things, swapping rows, multiplying a row by a non-zero constant, or adding a multiple of a row to another row, these are all legal. They will not change the answers to the system. These are called the row operations. And so the idea is the following. Jeez, today was all definition. The idea is the following. There are times when you have a system that we want to solve. One way in which we can do this, which by the way is the way your calculator does it. So you plug in a system into a TI-89, what it does is it augments the system. It transforms that system into a matrix where it just knows the first column is the x, the second column is the y, etc. Then it performs row operations to bring that matrix into a reduced or echelon form. The reason why it does reduced or echelon form is that row echelon form is not unique. Reduced or echelon form is. So it'll bring it to reduced or echelon form. And from that form, it'll be very easy for the calculator to tell you what the answers are. Because you'll have everyone zeroed out except the one variable that it needs to solve for, right? Or you'll have as close to that situation as possible. And we'll kind of talk about the cases. There are 3 cases that can happen there, but we'll talk about that. That's basically the idea of solving systems via this idea. 2 more names, and then we're out of here. When row reduction is used to put a matrix in REF, we say we've done Gaussian elimination. If we put it in reduced row echelon form, we say we've done Gauss-Jordan. This is just the name of two mathematicians that did a lot in linear algebra, which includes the study of matrices and a lot of other stuff. So basically, I can now say the phrase, you give your TI-89 a system of equations, it solves this by a Gauss-Jordan elimination. That's the method that your calculator uses. It's far more efficient than the method that you learned in high school, especially when the matrices start getting bigger and bigger and bigger. Yeah, we'll do more examples next time, but I had to get a lot of the vocabulary out of the way. When I'm talking about this stuff, you're going to need to know the phrasing. So we'll stop there. I'll see you on Thursday where we'll do a lot more definitions.
Oh, great. I should have
Not definitions, more examples, like actual computations.
You mean we're gonna be doing math in math
We're gonna be doing math in math class, yeah.